We'll wait for it to close.
Good.
Whoops. All right.
Good afternoon, ladies and gentlemen. Thank you for coming. My name is Xavier Medina. My teammates are Fernando Lopez and Gianfranco Pisani. Our faculty advisor is Dr. George Julie Kravitz. We are here to explain our senior project, which is the optimization of a radial compressor. Okay, so for our project, we have different objectives. One of them is to create a new blade design for the whole compressor site. We're gonna test the model on CFD. We want to improve the pressure ratio so we can get a better difference in pressure from the inlet to the outlet. We want to reduce the cost of the manufacturing of the whole wheel, including the housing. We want to create a CNC model because that's the manufacturing process we want to use, and we want to reduce the boost, the turbo threshold, so the turbo takes less time to be able to produce boost. So our design has to be high efficiency in the whole operational range. So all through the RPMs of the car, the compressor has to be able to perform perfectly. We want to increase the pressure ratios, as I just said, between the inlet and the outlet. We also want to reduce the turbulence condition inside the compressor housing, and we want to reduce lag in order to have more responsiveness. Here we have the blade design. It's made with 10 blades. The blades that are shown there are just the main family. There's going to be another family that's going to go between the big blades. It's not shown here, but it's going to include that. We have the two parts. We have the inducer and the exducer. The inducer is the top part. If you make it like a circle, that's called the inducer, and the exducer is the bottom part, the whole circle. So regarding fluid dynamics, we have the continuous equation from Euler, and this, here we can see that there is a difference in area at these 2 points. And the continuous equation says that every mass that gets into a system has to get out. So here we change the area. So from here in the steady state, we see that the mass flow rate is this is the velocity times the area. So if we reduce the area, we're gonna have higher speed. But if we increase the area, we're gonna decrease the speed, increasing the pressure, because when the velocities drop, we increase the pressure. Here is represented the cutaway of the whole system. We have the blades and the housing, and here you have video of the design. There's no.
As you can see, it moves. We have forward facing blades, so it causes a higher pressure difference. So our design objectives are ultimately to create a better, more efficient centrifugal compressor, because it causes a higher efficiency in all of our engines. So we can therefore downsize our engines so we can increase our power output with the same displacement of our engine. So a global component of our design is that our car manufacturers nowadays are using more and more turbochargers. So I read that by 2020, the majority of cars are going to be turbocharged, and they're going to be in a smaller displacement, ranging from like the 1.3 liters to 2-liter engines, and with 3 or 4 cylinders. The market for this is increasing gradually. It's 18.3% of gasoline turbochargers market has increased, and the diesel turbocharger has also increased. Key companies too that use turbochargers and that create turbochargers is Honeywell, and that's the main one that owns about 60 to 70% of the market itself right now. And we have all the other companies too. Here's our timeline for our project. Right now we're the green stages. We've conducted most of our research already, and we've already made several CAD models. And here's our cost analysis. It's overinflated right now, mainly due to labor costs of man hours. So right now our cost is at $4,964, but it's mainly man hours and computed costs. They're just very estimated numbers.
All right, so the manufacturing methods, we know that there are 3 methods that we can choose from. There's injection molding, which is profitable and it's better for mass production. So that is what most companies use nowadays because it's for mass production, for commercialized parts. And then casting is another method that we can use, but for us, for our project's application, we are going to go ahead and use CNC modeling for a few reasons. One, machining practice, it helps us better affiliate ourselves with actually being able to use
the CNC machinings and models and helps us to further our education. 2, it is the available manufacturing method that we have on site, and we will be able to use that with conjunction with Zuccarelli, with Richard Zuccarelli. And it also gives better material uniform composition of the 3. And now, for the housing, it has been determined that we will be using the Mitsubishi TD04 housing component, and the impeller will be designed abiding the housing's dimensions. Now, for testing, we want to first go through ahead and put it through computational fluid dynamics. Then after that, we will go ahead and put it through the Mode Frontier optimization program to optimize design parameters. Once the design has been chosen, our best bet is to create the design, make a prototype, then run it and fit it in with an electric motor just to make sure that we have all our clearances nice and it's running smoothly and it's not having too much play or anything. And then our future testing, and hopefully the best testing that we can have, would be to fit it into one of our teammates' cars in his turbocharger and see if we can actually have real-world application and real-world performance improvements. Any questions? And we'd like to acknowledge Dr. Julius Kravich and the Maid Rock Lab. Questions?
I got none. Good job.
Thank you very much. Appreciate it. Any questions from the back? Thank you very much.
All right.